Last lecture we talked about work. Now we're going to talk about the other mechanism by which energy can transfer from the system to the surroundings or vice versa, and that's heat. Work is a mechanical means of transfer. There's some force, there's some displacement. For the PV case, the force is usually pressure, and the displacement is usually some kind of volume change. But heat is a completely different kind of thing. At the microscopic level, it's still mechanical. Everything's mechanical at the microscopic level. But it's not a flow that's pushed or caused by force. It's something that happens on its own. It's energy diffusion. So on the microscopic level, a heat flow looks like this. You've got some molecules on this side of the barrier, and they have a certain amount of kinetic energy, let's say. Usually it's mostly kinetic energy that represents heat. There are other contributions, but mostly it's kinetic energy. And this long arrow here represents, let me change color, represents the velocity of this particle. It hits the wall, and in the course of hitting the wall, it loses some of its energy. It transfers some of its energy to the wall. And so it bounces off with less velocity. It lost some energy. And then inside the wall, all kinds of vibrations take place, but because there's higher energy here to start with, the net result of all those vibrations is that the energy tends to transfer across the wall. And then on the far side, a particle or a molecule with relatively low kinetic energy here hits the wall, and as it hits, a vibration bumps it, and it leaves the wall with more energy than it came in with. And so the net result is a flow of energy across the barrier, even though there's no direct mechanism by which that energy is transferred. We will see that in practical calculations, the heat flow is exceedingly important. It's very closely related to S. In fact, let me say that the change in entropy is a reversible heat flow divided by T. So heat flow and entropy are very closely related to each other. And you can kind of see that in the discussion above. All these flows of energy are taking place on their own, right? And that must mean that the number of microstates available is greater as the energy moves across the barrier, that the energy moving from here to here within the wall, say, for example, opens up new microstates and therefore is statistically driven. And if that's true, then of course heat flows are going to be related to entropy, because basically heat flow in that case is an effect from entropy, an effect of statistics. Yeah. How do we calculate entropy? We did a lot of calculations with work. Work is physical and therefore relatively straightforward to talk about. For heat, because there's no physical force, no real physics involved, the only general method for calculating a change in heat or a heat flow is to take the overall energy change and subtract the work. The work we know how to calculate, but this requires that you have some independent, separate way of calculating what the energy flow is. Sometimes you do, and then this works just fine. And there are cases that come up, we'll talk about them actually before very long, where this is the only method available to you. But probably the most common case where there's a heat flow is that the heat flow is caused by a temperature difference. So you've got, for example, a box, and it's at a temperature T1, and then there's a surroundings out here, but that surroundings is a little hotter. It's at T2, and the difference in temperature drives heat across the barrier or the boundary, and pretty soon you've got more heat inside than you had before. That's a temperature difference, and in the end, the temperature inside the system then starts to match the temperature outside, and so the temperature in the system itself rises. That's a temperature-driven heat transfer. And there is a good way to calculate that. It's using something called the heat capacity. I think probably everybody has used these before. Freshman chemistry uses heat capacity calculations, for example. So dQ is equal to heat capacity times whatever the temperature rise is. That means that the heat capacity is energy change or heat change per unit temperature, right? It's how much energy can you store in the system for a 1 degree rise in temperature, let's say. The heat capacity depends in general on temperature. If you warm something up, its heat capacity changes, but intuitively you would think it doesn't change very much, and that's generally true, unless a phase transition occurs or something like that. If some dramatic change happens, then the heat capacity changes. But if nothing dramatic happens, then the heat capacity is a very weak function of temperature. It barely depends on temperature. In the general case, then, the overall total heat change is the integral of the heat capacity with respect to temperature over the whole temperature range. But in most cases where the heat capacity is itself a constant, or nearly a constant, the heat change is just C times the temperature change, even when the temperature change is pretty big. This formula is usually good for delta T less than or equal to about 50 degrees Kelvin or 50 degrees C, either one. Beyond that, if it gets bigger, if the temperature change gets bigger than about 50, well, then you're likely to start having phase transitions take place and stuff, and then the formula is no good at all. But also, over a bigger temperature range, the temperature dependence of the heat capacity starts to matter a bit too. Okay, there are two kinds of heat capacity. Well, there's actually more than two kinds, but there are two standard kinds of heat capacity. In the first case, the heat capacity at constant volume, CV, is the heat capacity that occurs, as the name implies, when the system doesn't change its volume. So a temperature rise takes place, T goes to T plus dt. Some heat flows as a result of that, and no volume changes take place, then CV is the thing to put in. You can look these values up in tables. And the tables will oftentimes have a CV, and then they'll also oftentimes have a CP. That's the number that applies if you're at constant pressure. So you've got a P bath outside. The volume of the system can change now. Heat flows in when a temperature rise occurs. And in that case, you have to, the effective ability of the system to absorb heat is different than in the constant volume case. And so you got to use a different value of the heat capacity. It's CP. Why is CP different than CV? In fact, CP is always bigger than CV. Why is that? Well, it's because in the constant pressure case, the volume of the system is changing against an outside pressure. And that means the system is doing work at the same time. So the energy is coming in as heat from one direction and going back out as work in the other direction. And that means it's harder to raise the temperature in here, right? If you want to ask how much heat do you have to put in order to get a 1 degree rise, well, half the heat's going back out as energy, as work. So you got to put twice as much, let's say, heat energy in order to get the same temperature rise. So CP is always greater than CV. For an ideal gas, CP is equal to CV plus N times R. For a general system, there's a relationship. It's fairly complicated. It involves the isothermal compressibility and the thermal expansion coefficient and that kind of thing, and CV itself. And I won't give it because it's rarely used. I've never actually used it in a practical situation in my career. And this is the one that's actually by far the most commonly used. And part of the reason also that formula isn't very widely used is for liquids and solids, there's very little volume change, right? The temperature changes by 1 degree, okay, the water expands a tiny bit, but that doesn't do enough work to make any real difference. And so in that case, the heat capacity at constant pressure is almost the same as the heat capacity at constant volume, and people just don't bother with the small difference. The heat capacity is an extensive quantity. It depends on how big the system is. If you've got a system of a certain size and you double it, your heat capacity is also doubled. So it's like energy or volume or mole numbers. It doubles when the system doubles. It's not like temperature or pressure or molar volume or something like that where the quantity stays the same even when the system doubles. Heat capacities, normally when we're talking about heat capacities of a substance, we're thinking about something called molar heat capacity. That applies to a pure substance. But if you've got some system that's got all kinds of internal inhomogeneities, so a box of rocks, for example, there's still a heat capacity for that. It doesn't matter how complicated or messed up it may be on the inside. You can still talk about how much heat it takes to raise the temperature by 1 degree, and therefore there's a heat capacity. So the heat change for this complicated case is whatever the heat capacity is for the box of rocks times dT, and same thing for the water case over here. But in the water case, you can talk about the molar. You can't really talk about the molar heat capacity for rocks, right, because there's a whole bunch of stuff in there, a whole bunch of different stuff in there, and there's no single substance you can even identify necessarily. But in the case of pure water, you can look up in tables a molar heat capacity. The little m there means molar. And then the total heat capacity is however many moles you've got times the molar heat capacity, of course. There is a related quantity called a specific heat, which is probably the thing most people have seen most often. It's probably the most widely used form of heat capacity, in fact. And there you have a heat capacity per gram of whatever it is you're talking about. And so it's the mass in grams times the specific heat that gives you the total heat capacity. Okay, let's do some examples. Let's suppose you have some stuff in a box that we won't bother to say what the stuff is because it doesn't matter for the present purposes. We say that it's got a fixed volume, this box does, so the heat capacity at constant volume is what we want. We're saying that there's 10 moles of stuff in there, whatever it is. We're saying that the heat capacity per mole at constant volume is 20 joules per K per mole. Note the units there. And I might note in passing that these units here are exactly the same as the units for the gas constant, and also the same, we haven't talked about entropy really yet, but the same as the units for entropy. So heat capacity, gas constants, and entropy all have the same units. And let's say the temperature is changes 50 degrees. Then the heat change, the amount of heat absorbed by the box, so the heat went up, notice, and that means heat went in, warmed the box up by 50 degrees, is 10 moles times 20 joules per K per mole times 50 degrees Kelvin, and that's 10,000 joules or 10 kilojoules. Here's another case, but for a constant pressure case. Cp is N times the heat capacity per mole at constant pressure. That's always a little bigger. I mean, I just picked numbers out of the air for this example, so I picked 28 here. That's a pretty typical number, actually. And delta T of 50 again, 10 moles, 28 joules per K per mole, and 50 degrees gives you 14 kilojoules. All right, that's it for today, and we'll stop there.